I mentioned repeated eigenvalues in the previous video, but I didn't really tell you what that meant. And we're going to see it now. We have a system, x prime equals the matrix 12, negative 9, 4, 0 times x. We're to find the general solution of the system, and we start by finding our eigenvalues. And so 12 minus lambda, negative 9, 4, negative lambda equals 0 gives us lambda squared minus 12 lambda plus 36 is equal to 0. That's going to give us lambda minus 6, the quantity squared, is equal to 0, and so lambda is equal to 6. That exponent on the factor of lambda minus 6 is what makes the eigenvalue repeated. This is lambda equals 6 repeated, and in particular we would say that the multiplicity is 2. Technically it's the algebraic multiplicity. All you care about is that it's 2. Continuing with the procedure that we've gotten used to here, lambda equals 6 is going to be plugged into a minus lambda I, giving us a vector 6, negative 9, 4, negative 6 times k is equal to 0. We can see that this boils down actually to 2, negative 3, 0, 0 times k is equal to 0. That gives us the equation 2k1 minus 3k2 is equal to 0, or k1 is equal to 3 halves k2. Letting k2 equal 2 gives us the vector k is equal to 3, 2. And we have a solution x1 is equal to 3, 2, that column vector, e to the 6 lambda. But that's all we get out of this. We don't have a second solution. We know we're expecting one because this is a 2 by 2 system. I'll first point out that this solution has the form x1 is equal to k e to the lambda t. It turns out that the form of x2 is x2 is equal to k t e to the lambda t plus p e to the lambda t. Before, when we had repeated roots to an auxiliary equation, we would augment a second solution by including a factor of t. Here it's a little bit more complicated. The second solution has two terms, one of which has t. That t in there in front of k in the term e to the lambda t makes that part of x2 linearly independent with x1. As for the pe to the lambda t, oh, that p is a vector. As for the pe to the lambda t, what I'm going to do is justify that this form of solution actually works. And in so doing, I'm going to show you how to find p. Starting with this form of x2 and differentiating using the power rule as appropriate, we get x2 prime is equal to ke to the lambda t plus k lambda t e to the lambda t plus p lambda e to the lambda t. X prime equals ax, the equation or the system that we've been solving, then becomes the quantity of k plus k lambda t plus p lambda all times e to the lambda t, that's our x prime, equals a times the quantity of kt plus p all times e to the lambda t, that's a times x. We can drop the e to the lambda t's, and getting everything on the same side and putting like terms together, we have ak minus lambda k all times t plus all the terms that don't have t in them, remembering to distribute, the quantity of ap minus lambda p minus k is equal to the 0 vector. since we have 0 on the right-hand side, all the expressions that are the first power of t on the left should add up to 0, and all the constant terms on the left should add up to 0. That's going to give us that ak minus lambda k is equal to 0. Factoring out that k, we have a minus lambda I times k is equal to 0. We already knew that. The new terms here that have p in them give us ap minus lambda p minus k equals 0, but I'm going to write it as equals k. And then we have a minus lambda I times p is equal to k. What this tells us is once we've found k, we can use it to find p. We then form our solution x2, and that together with x1 gives us the general solution. Here our k is 3, 2, and a minus lambda I, when lambda was 6, was 6, negative 9, 4, negative 6. We always have to use that form of the matrix. So this gives us 6, negative 9, 4, negative 6 times p is equal to k, which we know to be 3, 2. This leads to a different augmented matrix, and I have to actually write down what's on the right-hand side this time because it's not just zeros that never change. Our augmented matrix has rows 6, negative 9, 3, and 4, negative 6, 2. You may notice that these both boil down to 4p1 minus 6p2 is equal to 2. And here p1 and p2 are the entries in the column vector p. Well, that means that 2p1 minus 3p2 is equal to 1. Any values p1 and p2 that satisfy this relationship will give us a valid vector p. Before, when we were doing this with the k's, when we had k1 equals 3 halves k2, if we let k2 equal 0, that would force k1 to equal 0. That would give us the 0 vector, but an eigenvector is never allowed to be the 0 vector. Here, though, we have 2p1 minus 3p2 equals 1. We can let either one of them be whatever number we want, including 0. So what I'm going to do is I'm going to let p2, man, these p's are hard to write, equal 0. Then we get that p1 is equal to 1/2. Yeah, it's a fraction. Sometimes there's just not a way around that. And then the vector p is 1/2, 0. Putting this all together, we get x of t is equal to c1 times 32e to the 6t. That's our c1 x1, which is really c1 k e to the lambda t. Second solution, c2 times. It's 3, 2 t e to the 6t. That's going to be our k t e to the lambda t plus 1/2 0 e to the 6t, and that's plus our p e to the lambda t. Of course, that p is a vector. I'm going to recap and then actually extend what we just saw. If lambda is a repeated eigenvalue, and we have only k as an eigenvector, then x1 is going to be k e to the lambda t, and remember that we get k by solving a minus lambda I times k is equal to 0. x2 is kt e to the lambda t plus p e to the lambda t, where a minus lambda I times p is equal to k. So we use p to to find k. If our eigenvalue is repeated more times, let's say 3 times, it's a multiplicity 3, then we have an x3 solution. And it has the form k times 1/2 t squared e to the lambda t plus p t e to the lambda t plus q e to the lambda t. We keep picking up more and more terms, and this 1/2 t squared ensures that we are linearly independent with x1 and x2. The q vector is found by solving a minus lambda I times q is equal to p. So it's actually called a Jordan chain, but we use k to find p when we need to. And then if we need to, we use p to find q. This process can go on for a long time if we have eigenvalue of multiplicity 5. The general term here is not just like, say, a 1/2 t squared. It's actually 1/2 factorial t squared. And now you know how to handle it. If you had a 3 there, it would be t cubed 1/3 factorial. And then we would use q to find some vector, maybe r, and just keep extending this. If somebody assigns that to you, like, they're not really your friend, right?